Hello everyone, welcome to MindMatrix. So here we are back again with the third lecture on operating system. So let's start. Before starting, let me introduce myself. My name is Anshul Sharma. I'm upcoming software engineer too at Juniper Networks. Currently, I'm pursuing M.Tech from IIT Kanpur in computer science. I have more than 2 years of teaching experience, mentored more than 1,000 students as of now, and expertise in computer science and data science subjects. If I talk about the achievements, I have secured All India rank 294 in GATE Computer Science, cleared ISRO NIC NAILET exam, and got selected as Administrative Officer at AIC. So guys, everyone, those who are watching this lecture, you can join our doubt discussion Telegram group. So you can scan this QR code and you will be able to join our group where you can ask your doubts if you have any. And also we will be sharing the PDFs of all the lectures that we are, taking on YouTube. Clear? So let's start. So in the previous lectures, we talked about process, right? Now we are going to talk about dual mode of operations in operating system. So we have two modes of operation. One is your user mode and other one is your kernel mode. So let's talk about it one by one, right? So what is user mode actually? When the computer system runs user app, then the system is in user mode. So we have many user applications, right? So whenever we want to run those applications, system will be in the user mode. When the user app request for a service from the operating system, or an interrupt occurs due to some reason on the system, or we have invoked some system call, in that case there will be transition from the user mode to the kernel mode. Clear? So to run the user applications, the system has to be in the user mode. When we want some service from the operating system, in that case, there will be a switch or there will be a transition from the user mode to the kernel mode. Clear? Now how this transition happens, let's understand this. So here we have this user mode and here we have this kernel mode. So we have, to explain you in a better way. So this diagram is very useful. Carefully observe this. When the system is in user mode, the mode bit, so MB here represents mode bit. So mode bit is set to 1 when the system is in user mode. Clear? So user executing the process, fine. Then let's say your code, let's say you have called a printf. You are, executing a printf statement. So we know this, that printf basically invoke a write system call, right? So now if it is a system call, that means OS intervention is necessary. Clear? So we are invoking a system call. Now when we invoke a system call, OS intervention is necessary. In that case, that means we need a service from the operating system. So we need to switch, we need to transit from user to kernel mode. So first we are going to set the mode bit to 0 before switching the mode, and then when now we are in the kernel mode where mode bit is equal to 0, we are going to execute the system call. Okay, so in this case we have considered the example of a system call. It may be some other service from the operating system or an interrupt if it is there. So it can be any case, right? Here we are considering the system call execution. Now system call execution will be done, and then we are going to basically the system is going to set the mode bit to 1 before switching back to the user mode. So now it is there in the return to the user mode. So in this way your transition happens from user to kernel mode and vice versa. So when we talk about in the last lecture we talked about context switching as well, right? So the context switching means we have to save the context of one process and we have to load the context of another process. We know what is context, all everything we have discussed in the previous lecture. You can watch that lecture if you are watching this lecture for the first time. I mean, if you are new to our channel. So we are saving the context, we are loading the context of another process. So context switching requires OS intervention, right? So if OS intervention is required, in that case again mode switch will happen. So first mode switch happens from user to kernel mode, then context switching occurs. After that again kernel to user mode will be a transition. Okay, so I hope it is crystal clear to all of you. Let's proceed further. What about kernel mode? When system boots, then hardware starts in the kernel mode. Whenever you start the system, always the hardware starts in the kernel mode, and then operating system is loaded into the main memory from the hard disk or the secondary memory. Then it starts user app in user mode. We have certain instructions, we call them as privileged instructions, that is handling interrupts, input output management, etc., that you execute only in the kernel mode. Clear? So as of now we have studied two modes of operation in operating system. One is user mode, other one is your kernel mode. Now we are going to talk about two types of instructions. One is privileged instructions and other one is your non-privileged instructions. So what are privileged instructions? So let's see here. Privileged instruction can run only in the kernel mode. Clear? You cannot run privileged instructions in the user mode because operating system intervention is required. We need service from operating system. Any attempts to execute privileged instruction in user mode is treated as an illegal instructions. Okay, basically if you want to get the intuition behind it, why we are having two modes. So we want our operating system to be secure also, right? We want the services that is being provided by the operating system to be secured, and it should not be, accessed by any user application. So that's why we have divided these two modes, okay, to make our system more secure. Clear? So that is the intuition behind it, to in order to have two modes of operations. So if you talk about privileged instructions, they can execute only in the kernel mode, and if you execute any privileged instruction in the user mode, in that case it is going to be treated as the illegal instruction. And if it is treated as the illegal instruction, in that case hardware traps it to the operating system, then operating system will take care of it, and it is not, obviously it is not going to allow accessing it or executing that instruction. Any instruction that can modify the contents of the timer is a privileged instruction. Clear? Privileged instruction, so basically here we are written P instruction, that means privileged instruction are used by the operating system in order to achieve correct operation. Fine. Now there are some examples here of privileged instruction: input output instruction, halt instruction, turn off all interrupts, setting the timer, context switching, clearing the memory, modifying entries on a device status table. All these are the examples of privileged instructions. Clear? Let's proceed further. Now let's talk about non-privileged instructions. So we can run non-privileged instruction only in the user mode. And there are certain examples like reading the status of processor, reading system time, generating any trap instruction, sending final printout of printer. All these are the services that is where we don't need operating system intervention, so we can run them easily in the user mode. So these are the examples of non-privileged instructions. I hope it is all clear to you. Let's proceed further. Now we are going to talk about system calls. So in the last lecture, we have seen how fork system call executes, and what is the functionality of fork system call, how it creates child process, and we also solved many examples based on that in the previous lecture. So I hope you have visited that as well. Now we are going to talk about another system calls that we have in the that we use sometimes. So programming interface to the services provided by the operating system calls are accessed by programs via high level API. So basically using a high level API, we can access our programs can access the system calls, and they can invoke it in order to render any service, in order to access that kind of service. Basically I gave you the example of printf statement, is it uses write system call, we have fork system call. So all this can be accessed by the programs using a high level API. I hope you know, that is application programming interface. Clear? There are certain types of system calls. So basically, in order to control the process, we have certain system calls. Here you can see we have fork, we have exit, we have wait, and much more. So I've given you the important and main examples. In order to manage the file management, so in that case we have these kind of system calls: open, read, write, and close. Similarly, for device management, we have certain system calls, right? Set console mode, read console mode. Then for information maintenance, also we have certain system calls: get, PID, alarm, sleep, right? And for communication purpose, for communication between the processes, we also have certain system calls like pipe and map, or SHM, get, that is create file mapping. For protection as well, we have certain system call, that is ch mode, set file security, chon, that is set security descriptor group. So these are not very important. Certain system calls are not very important as per your gate exam point of view, but you should know at least some of them, that fork or wait, exit. These are certain system calls that you need to know, because sometimes they ask questions, and in the previous year also they asked a few questions based on system calls. So that is very important, and we will be covering the questions as well in the upcoming lectures, okay, when we will be solving previous year questions. So that was all about system calls, and now we are proceeding towards how scheduling happens, right? And what are the process states we have, what are schedulers. All these concepts we will be discussing in this lecture now. So let's talk about process states. We know what is process. Now we are going to talk about its certain states. So the first state we have is new state. So when a program resides in the secondary memory, we can call that as it is present in the new state. Okay, we can call that as it is present in the new state. Now from the secondary memory, we load the program to the main memory. So basically there is a transition from new to ready state. So here the process is present in the main memory, so we call that state as ready state. So program is ready to execute, but it is not executing as of now. Okay, then what happens is, then we have this short-term scheduler. So basically we have three types of scheduler: long-term scheduler, short-term scheduler, medium-term scheduler. We will be talking about all these schedulers in detail in this lecture only, but just understand this, that your long-term scheduler controls the degree of multi-programming. What is degree of multi-programming? Degree of multi-programming means the number of processes that can reside, the maximum number of processes that can reside in the main memory, that is being controlled by your long-term scheduler. So basically long-term scheduler loads the program from the secondary memory to the main memory. Okay, so the transition is going to happen from new to ready state, and the system is going to use the long-term scheduler for that purpose. Okay, then from ready to run state means the program is executing, the program is running. Okay, that means the CPU is allocated to that particular process. Now your short-term scheduler, see, let's say you have 10 processes present in the ready state or in the main memory. Now out of those 10 processes, you have to select one process that you are going to allocate CPU to it. Clear? So it is the responsibility of the short-term scheduler to pick one process, or to select one process out of all the processes present in the main memory. Clear? And then it is going to select it. Then it is the responsibility of the dispatcher. Carefully understand these concepts. Then it is the responsibility of the dispatcher to shift that process from the ready state to the run state. So long-term scheduler controls the degree of multi-programming. It loads all, or it selects all the processes that has to be loaded into the main memory. Then short-term scheduler will pick or select one process out of those processes present in the main memory, and that one selected process will be dispatched by your dispatcher from ready to run state. Clear? And now the process is going to execute in the run state. Clear? So after run state, if the process execution is complete, then it is going to go to the terminate state. Clear? But sometimes there may be a case when your process needs to perform some input output operation. Yes, possible. Let's say your process wants to access a printer or some, to store some information in the memory. So input output operation is required, clear, by that process. So in that case, let's say a process is executing, now input output operation is required. In that case, from the run state, this it is going to shift the process to the wait or block state, and this wait or block state is still in the main memory, but the process is not executing now. It is going to perform all the input output operations, whatever is required by that process. It is going to perform, while it is in the wait or block state, but still it is in the main memory. Clear? Keep this in mind. Clear? So all the input output operations will be performed, and let's say if it is going to complete, let's say if it is going to complete the input output operation, then it is going to go back to the ready state. So if input output completion is done, input output is done, then it is going to go to the ready state, and then again it will be selected by short term scheduler, and dispatcher will again dispatch from ready to run state, and then it is going to execute further. So this is one way of performing input output operation. And now let's understand this also. Let's say your process are performing input output operation, your processes are performing input output operation when they are in the wait or block state. But let's say due to some reason your main memory is fully occupied. Now you want to just free it so that other processes can also be accommodated in the main memory. In that case, when your main memory is out of space and you want to accommodate more processes in the main memory, in that case the processes which are performing input output operations, you will be shifting those processes from wait or block state to the suspend wait, and that is going to be done by your medium term scheduler, the third scheduler. Clear? So that is being done by the medium term scheduler. So basically medium term scheduler is responsible for swapping. Now this is one new term for you, swapping. Swapping means shifting the process from main memory to secondary memory, shifting the process from main memory to secondary memory. So as you know, when the process was performing input output operation while it was in the main memory, in that case when the main memory is running out of space, in that case we medium term scheduler is going to swapped out the process that is there in the main memory, which is performing input output operation, to the suspend wait, which is there in the secondary memory. And now your process can all perform input output operation here as well. It's not mandatory that a process has to be in the main memory, then only it can perform input output operation. No, when it is there in the secondary memory, then also it can perform input output operation. And then here you can see when input output is completed but still it is in suspend mode, so it is going to go to the suspend ready. So from suspend wait, either it can go to back to the waiting or block state, right, if there is a space in the main memory. If there is no space in the main memory, in that case after input output completion, it is going to move to the suspend ready state, and then from there on it is going to go to the ready state, and again short term scheduler will pick that process, select that process, dispatcher will move the process from ready to running state, and so on. Again the same cycle goes on. Clear? So from suspend wait it can move to wait or block state, either wait or block state, or to suspend ready state. Again suspend ready state is there in the secondary memory. Clear? So this is the flow, right? Now, one more thing you can observe here, that from the ready state, the process, let's say you have many processes present in the main memory. Okay. Now, if you want to free the main memory, then you can shift the processes from the ready state directly to the suspend ready state as well. That means you can shift the process from main memory to secondary memory. So we can suspend the processes. Clear? And then again, if you want some processes, you can those the processes which are present in the suspend ready, you can take it back to the ready state, so you can resume them. Clear? So this is the flow. Now one more thing here we need to observe, when we say preemption, when we talk about preemption, what is preemption? In the last lecture also I explained you a little. So preemption means, let's say one P1 process is executing, and let's say the time quantum you have decided is for 2 millisecond. Then after 2 millisecond you are going to preempt this process in order to execute another process. Clear? So preemption means basically context switching will happen. You will take the CPU from P1 process and you are going to allocate the CPU to the another process that you want to execute. So this is preemption. Clear? This is preemption. Now in case of preemption, so basically there can be many cases. Let's say time quantum is 2 millisecond. After that you are going to give the CPU to another process. That in that way, in that case also preemption can occur. Or if some high priority process, let's say P2 is high priority process, P2 is high priority process, in that case also you are going to preempt P1 process that is currently executing. That means you are going to take the CPU back from the P1 process and you are going to allocate it to the P2 process. Clear? So here you can see when your process is in the running state, so either due to the time quantum, or if high priority process arrives, in that case you are going to preempt P1 process. So you are going to shift the P1 process back to the ready state, and when this high priority process is going to execute completely, or let's say when there is no process running, in that case your dispatcher again will shift P1 process from ready to run state. So that again the same cycle goes on. But this is very important. This is all for preemption. Let me write here, this is in case of preemption. If there is no preemption, that means let's say if you are not allowing preemption, in that case this arrow will not be there. From run to ready state, the transition will not be present in case of no preemption. I hope it is all clear to you now. What are the process states? How the transition happens from one state to another state? What is the responsibility of long-term scheduler? What is the responsibility of short-term scheduler and medium-term scheduler? We are going to see schedulers in details also in the upcoming slides. But I hope this transition, this process states diagram is clear to all of you. Right? Let's proceed. So if we talk about further in process states, a process necessarily goes through minimum these states, right? So that means a process has to go through new state, ready state, run state, and terminate state, right? So minimum these 4 states a process has to go through, necessarily has to go through, right? Then processes requiring input output, minimum number of state is 5. Let's say if your process needs some input output operation, need to perform some input output operation, minimum number of states will be 5. And what are that? New, ready, run. Let's say input output operation, minimum we are talking about. So wait and block state, back to ready state, then run, and then complete. So 5 states, minimum 5 states are required. A single processor can execute only one process at a time. If you have one processor, only one process can execute. That means there will be only one process present in the running state. Clear? If you have multiple processors, you can have multiple processes. That means one processor will be executing one process, another processor will be executing another process. Clear? So in case of single processor, or we can say uniprocessor, only one process will be executing at a time. Moving a process from wait to suspend wait is a better alternative, as the process is already waiting for some blocked resource. Clear? So as we saw here, that from wait to block state we are moving it to suspend wait, right? So it is a better alternative. How we can say that? As the main memory will be having some more space to accommodate another processes, and as the process is already waiting for some blocked resource, or it is performing some input output operation. Context switching, I already explained you in the previous lecture, process of saving context of one process and loading the context of another process. Context switching happens when a high priority process comes to the ready state. Explained you. An interrupt occurs. If any interrupt occur, then also context switching can occur. User and kernel mode switch. User and kernel mode switch. In that case, also context switching happens. And the fourth one is preemptive CPU scheduling used. That means in case of preemption as well, context switching will occur. Clear? Now there are two types of processes, CPU bound and input output bound processes. What are CPU bound processes? So CPU bound processes require more CPU time or spends more time in a running state. That means they are very intensive in CPU operation. Okay, they are very intensive in CPU operation. And what about input output bound processes? They require more input output time, more time in waiting state. They are more intensive in input output operations. They want to perform more input output operation as compared to CPU operations. Clear? So these are the two types of processes, CPU bound and input output bound process. Now this is very important. Mode switch time is less than context switch time. So as I explained you in dual mode operations diagram, that in order to perform context switching, first you need to perform mode switching. Correct? First you need to perform mode switching from user to kernel mode, and then you are going to perform context switching, then from kernel to back to user mode. So obviously the mode switch time will always be less than context switching time. Clear? Clear? So this is also very important. What is multiprogramming? I explained you a little in the previous lecture, but here you can clearly see this. Multiprogramming, when you have multiple processes in the ready state, that means in the main memory. Clear? Now there are two types, with preemption, non-preemption, or without preemption basically. With preemption, forcefully removed processes from CPU. So if we have allocated CPU to one process, we are going to forcefully we are going to take back the CPU and allocate it to the another process. So that is basically time sharing or multitasking. So I explained you that multitasking is an extension of multiprogramming. Is an extension of multiprogramming. And if there is no preemption, in that case, not removed until execution. So until you completely execute the process, you are not going to take CPU back from the process, currently executing process. Clear? Now what is degree of multiprogramming? Degree of multiprogramming is the maximum number of processes that can be present in the ready state, that means in the main memory. This is degree of multiprogramming. Optimal degree of multiprogramming means average rate of process creation is equal to the average departure rate of processes from the main memory. That means you can say the number of processes, approximate number of processes that you are creating is equal to the number of processes that are completing their execution and they are just moving out from the main memory. So that is the optimal degree of multiprogramming. Clear? Now let's talk about schedulers. This is very important. So schedulers help in scheduling the processes in various ways. Responsible for selecting the jobs to be submitted into the system and deciding which process to run. So this is the responsibility of schedulers. And we have three types of scheduler. Let's talk about types of schedulers. The first one we have is long-term scheduler, which controls performance basically. Okay, so long-term scheduler is also known as job scheduler. It selects a balanced mix of input output bound and CPU bound processes from the secondary memory, that means in the new state, then it loads the selected processes onto the main memory, that means the ready state for execution. So in case of long-term scheduler, it is going to select a well mixed of CPU bound processes and input bound processes. That is also necessary, right? If it is going to select all the CPU bound processes, in that case, many input output devices will remain idle, right? And the input output bound processes will not be able to execute. Clear? So it is very important that it selects a well mixed of CPU bound and input output bound processes, so that CPU will also be busy in executing the processes, and input output devices will also be busy in performing input output operation for these input output bound processes. Clear? So primary objective of long-term scheduler is to maintain a good degree of multi-programming. So from new to ready state, this is the primary objective of long-term scheduler. From shifting the processes from new to ready state, new that means in the secondary memory, ready that means they are in the main memory. The second short-term scheduler we have, which is responsible for context switching time, also known as CPU scheduler. So it decides which process to execute next from the ready queue. So basically it selects the process from the ready queue. After the short-term scheduler decides the process, then it is the responsibility of dispatcher to assign the decided process to the CPU for execution. Explained you already in the when we were discussing in the process states, right? The diagram. Primary objective of short-term scheduler is to increase the system performance. So it is going to select those processes which are which are more CPU bound, and accordingly basically it is going to select in a well proportionate way which process to execute next, whether the CPU bound process to be executed next or whether the input output bound process to be executed next. So it is going to select it, and based on priority as well. So all these factors will be included while deciding the process to be executed next. Clear? So because it impacts the system performance. Dispatcher, it is a software that moves processes from ready to run state and vice versa. Okay, so it is going to do that. Clear? From ready to run state, it is going to shift the process. That is the responsibility of dispatcher. The third scheduler we have is a medium term scheduler, which is responsible for swapping. So it swaps out the processes from the main memory to secondary memory to free up the main memory when required. So whenever we want to free up the main memory, we are going to swap the processes from the main memory to secondary memory. So when I say we are going to swap, that means medium term scheduler is going to do that. It reduces degree of multi-programming, obviously, because degree of multi-programming means maximum number of processes that can reside in the main memory. So if you are moving some processes from the main memory back to the secondary memory, that means you are reducing the degree of multi-programming. After some time, when main memory becomes available, medium term scheduler swaps in the swapped out processes to the main memory, and its execution is resumed where it left off. So from that point where it left off, the execution is going to resume. Clear? Primary objective is swapping. That means shifting the process from main memory to secondary memory and back to it. Swapping may be required to improve the process mix. Sometimes we may use swapping to have equal number of all good mix of input output bound processes and CPU bound processes. So this is the functionality of medium term scheduler. Dispatcher. A dispatcher is a special program which comes into play after the scheduler, and dispatcher takes the process to the desired state queue after the short-term scheduler selects the process. So here we can specify that it is short-term scheduler. Okay, then it is the responsibility of dispatcher to take the process from that ready state to the run state, or in case of preemption, from run state back to the ready state. This is the responsibility of dispatcher. It involves context switching, as I explained you, switching to user mode, jumping to proper location on the user program to restart that program. Okay, so whenever there is a preemption. That means context switching is going to happen in that case. Switching to user mode, all these will be done by your dispatcher. Okay, and if it is going to execute the program again, then jumping to that proper location, uh, that means the location where the next instruction has to be executed, that is being taken care of by dispatcher. If you see, in some, if you summarize this dispatcher and scheduler, so basically a dispatcher is a module that gives control of CPU to the processes selected by the short-term scheduler. It is a code segment and it is dependent on scheduler for working. There is no specific algorithm for that. Time taken is dispatch latency, right? Whatever time is taken by dispatcher, we call it as dispatch latency. The algorithm responsible for context switches, switching to user mode, this is there being done by the dispatcher. What about scheduler? It selects processes among various processes. There are three types of scheduler: long, medium, and short-term scheduler. They work independently, works on various algorithm, shortest job first, first come first serve, and there are many CPU scheduling algorithms. Time taken is negligible. Only work is selection of processes. So it has to just select the processes that has to be executed next. So that's it from this lecture. I hope you really enjoyed it. In the next lecture, we are going to talk about CPU scheduling algorithms one by one, and we will be discussing the important concepts along with the questions. So I hope you really enjoyed this lecture. So you can join our MindMatrix channel on WhatsApp. This is the link. You can join our Telegram doubt discussion group where we are going to give you all the updates and you can ask your doubts there. We are going to provide you the PDFs of all our lectures as well. And to join our doubt discussion Telegram group, you can also scan this QR code and you will be able to join that easily. So that's it from this lecture. Thank you everyone. Stay tuned for the upcoming lectures and make notes properly. And we are here to help you out. If you have any doubt, do ask in our Telegram group. We will be helping you, in resolving your queries. So thank you everyone. See you in the next lecture. Bye bye.